Okay, welcome back. In this segment, in this video, we're going to talk about a lot of important things, and it's going to be involving a lot of math and equations and different formulas. So please watch carefully, have your guided notes out, and be following along as we go through this video. Okay. Before I start, we're going to talk about, let me give you a kind of an overview of what we're going to talk about in this video. We're going to start by talking about how to calculate speed. Okay? Then we're going to calculate velocity. And then we're going to end the video by talking about how to calculate acceleration. Okay, each one of them are very different and require different equations. So we're going to show you what the equations are, and then we're going to plug some numbers in and use them. So have a calculator out and ready, and be ready to use it, and be paying attention. Remember, you can always pause the video if you need some time, or watch a segment over if you need to. But let's get started. Speed is an object's distance divided by time, and so you're going to see its formula, or the equation that you find speed with, is given. Some troubles with the board. It's given right here. So speed is equal to distance divided by time. Distance, if you remember, the metric system is measuring in meters, and time is always measuring in seconds. So the units for speed are meters per second. Speed is a scalar quantity. Scalar quantities show magnitude and not direction. So they can't provide information about direction. It's just a speed. It doesn't tell us direction. So it's like looking down at your speedometer and it says you're going 65 miles per hour. You're going 65 miles per hour, but you don't know your direction if you just look at the speedometer. So speed is a scalar. Okay, now let's talk about how to find average speed. Average speed is the total distance divided by the total traveled time. So again, a very important formula. Average speed is found by taking the change in distance. So again, let me remind you, this triangle we see in physics all the time. It means, well, it's a delta. It's a Greek letter delta. And it means, whenever you see it, it means, okay, maybe. There we go. It means change. Okay, another way of saying change, so the delta, well, how I always think about it, is final minus initial. Please write that down somewhere on your books, somewhere on the top, on the margins, on the bottom. Whenever you see this triangle, this delta symbol, think final minus initial, and it means change. So the average speed, coming back to this formula over here, is change in distance divided by change in time. Okay. Another way you can describe speed is by instantaneous speed. Instantaneous speed is the speed at a specific moment in time. So an example of this, how you could find an instantaneous speed, is by looking down at a speedometer, your car, and it says you're going 65. Well, that's your instantaneous speed at that moment in time. Now, yeah, of course it's going to change. But at that moment in time, you were going 65 miles per hour. Again, you have to get it from a speedometer. Okay, let's do a practice problem on this. Practice problem number 9, it says, John starts his trip at 10 a.m. He travels 130 miles and arrives at his destination at noon. There's a few parts to this question, so let's read part A. It says, what was, I don't think this is supposed to be, I'll fix that later. What was his average speed for the trip? Okay, so again, we're going to look at average speed for the whole trip. Let me solve part A up here. So average, I'm having a lot of troubles with the board. Let me see if I can get it to work. Average speed is equal to the change in distance divided by the change in time. Okay? So now let's plug in all of our variables that we know into this formula. So the delta distance, okay? Remember, it means final minus initial. What was his final distance? So it says he travels 130 miles. So 130 is going to be his final distance. His initial position was 0. So I'm just going to say it's 0, so minus 0, divided by the change in time. Okay. Well, his final time was at noon. So that's 12. Oops. 12 minus the initial time. He left at 10 a.m. So I'm going to minus 10. I hope this board works. Okay. I'll just write slower. So if we solve this formula, we get 130 on top divided by, what's 12 minus 10? Well, that's 2. And 130 divided by 2 is equal to 65. But we need to determine our units. What were we measuring distance in? And we were measuring the distance in miles. So I'm going to put miles on top because that's where distance was. Miles divided by, and on the bottom, for time, our time was measured in hours. And so I'm going to put hours down here. So 65 miles per hour. Another way of writing that is how we are used to seeing it, mph, for miles per hour. So that was his average speed, 65 miles per hour. Part B, what was his instantaneous speed at 11 a.m.? Now, how are we going to solve this one? Without more information, there is no way we know his instantaneous speed at 11 a.m. Okay. Don't know what happened there. Okay, so at 11 a.m. Remember, this was, if on part A, we found his average speed was 65 miles per hour. That means some of the time he had to be going faster than 65, and some of the time he was going slower than 65, but his average speed was 65 miles per hour. So on part B, his instantaneous speed, the answer to that is there's just not enough information. So I'm going to put not enough. Not, I don't know what's going on with the board, maybe it won't work. Not enough info. Okay? Unless it told us that he looked down at his speedometer at exactly 11 a.m., we would never know his instantaneous speed. Okay, let's go on. Let's talk about calculating velocity. So we've talked about speed. Now let's talk about velocity. How we calculate it. It says velocity is the change in displacement divided by the change in time. So it's not distance anymore. Let me remind you, this is displacement divided by change in time. And so the units for velocity are, again, meters per second, because displacement's measured in meters, and we're dividing it by the time, which is in seconds, so again, it's meters per second. Okay, so let's talk about velocity. Velocity is a vector quantity and has both a magnitude and a direction. So we're going to have both a magnitude and direction with velocity. Change in direction can either be positive or negative. So velocity can be positive or negative. It gets a little tricky, but follow me through a few of these practice problems and we'll get this down. But we're going to be using this formula right here. Average velocity is equal to the change in displacement divided by change in time. Or displacement final minus displacement initial divided by time final minus time initial. Okay, let's do practice problem 10 and hopefully we can make sense of this. It says John travels, I don't think that 2 is supposed to be there, from his home to point A, which is 100 kilometers away. It took him 1 hour. He then travels back home in the same time. Okay, so on part A it says, find John's velocity from his home to point A. So the first half of his travels, we're going to find his velocity. I'm going to solve part A up here. So velocity is equal to change in displacement divided by the change in time. Okay? So let's do the top part of this equation first, his change in displacement. Again, displacement final, which he went 100 kilometers away. So that's 100 kilometers minus his initial displacement at his house or his home. I'm just going to call that point A, or his initial displacement I'm going to call 0, because that's where he started from. Okay, so 100 kilometers minus 0. And the time, it said it took him 1 hour to get there. So the final time was 1 hour, and the initial time I'm going to say is 0. So if you look at this, we can solve it. 100 kilometers divided by 1, and we're talking about hours. So his velocity from his home to point A is 100 kilometers per hour. So he went 100 kilometers an hour. Now let's solve part B, which says, what is John's velocity on the return trip? Now this is where it gets a little tricky. Okay, his velocity on the return trip. I'm going to solve part B. Let's solve this one up in this corner. So again, velocity is equal to change in displacement over change in time. Okay, now if we look at his displacement, his final displacement on the return trip would be his home, which I called earlier the displacement of 0. So 0 minus his initial displacement was point A, which I called 100 kilometers away, so 100 kilometers, divided by the time, the final time to go back. It said he completed that in the same amount of time, which was 1 hour, so 1 minus, the initial time is always going to be 0. So we're going to get minus 100 kilometers divided by 1, so it's just kilometers per hour. So it's a minus 100 kilometers per hour on his return trip. Okay? Now let me talk about this for a second. Can you really go minus 100 kilometers per hour? No. What does this sign, negative sign, tell us? That tells us direction. The sign tells us direction. So on part A, on the first part of his trip was positive. But if he turned around and came back to the same spot, he turned directly around, he's going the other way, so that sign means he went back the other way. So that tells us he went the other direction. Okay, part C. Is his round trip speed and velocity the same or different? This is a good question. Speed, if we look at the formula, is distance divided by time. Total distance divided by time. Now if we take his total distance, wouldn't that be 100 there and 100 kilometers back? So 200 divided by the total time was 1 hour there and 1 hour back. So 2. So his totals, his average speed would have been 100 kilometers per hour. That would be his average speed. Okay. That we just calculated speed. Now let's talk about velocity. It's very different. For velocity, for the round trip, is change in displacement over change in time. Now let's look at change in displacement. His final displacement was at his house, which I called 0. His initial displacement was also at his house, which was 0. So he didn't have any displacement if you're talking about the whole round trip. and divided by time, the final time would have been 2 hours, the initial would have been 0. So we're talking 0 over 2, which is equal to 0 kilometers per hour. So you can see that speed and velocity are very different. Why is his velocity 0? Well, it's because he didn't have any displacement. He came back to the same spot in which he left. So he didn't really move. He didn't have any displacement. So that's why it was 0. So you can see that speed and velocity, very different in how they're defined and how they're calculated. Okay, let's go to part D. What is the average speed for his round trip? Well, we kind of just answered that, right? His average speed for the round trip is 100 kilometers per hour. Okay. Part E. What is the velocity for the round trip? The velocity for his round trip, we solved up here as well, was 0 kilometers per hour. Oh, I guess it was a multiple choice question. So the answer to part E would have been A, 0 kilometers per hour. So hopefully you see there's a big difference between speed and velocity and how they're defined and calculated. All right, let's go to practice problem 11. It says the average velocity depends on the total displacement, the distance between the starting point and the end point. We just saw that. This question says a car moves due east at 30 miles per hour for 45 minutes, turns around and moves due west at 40 miles per hour for 60 minutes. What is the average velocity for the entire trip? So I'm going to underline what it wants us to find, the average velocity. And this is for the whole trip. So let's draw the vectors for the trip. He went due east, which is 0 degrees, which is to the right, at 30. So 30 miles per hour. And this lasted for 45 minutes. Okay. Then it turned around, went 40 miles per hour, so slightly longer. So 40 miles per hour. And he did this for 60 minutes. Okay. What was the average velocity for the entire trip? Okay. What I always like to do is put the formula of what we're trying to find, average velocity. Average velocity is equal to change in displacement divided by the change in time. Now, the part that makes this problem kind of complicated is finding the change in displacement, because it gave us a speed and a time. So we don't really know how far he moved unless we do a little bit of math. So 30 miles per hour for 45 minutes. Notice how the units are different. This one's measuring in hours, and it told us that the time was measured in minutes. What we need to do is take his miles per hour, the speed, and times it by the time, but the units have to be the same. So 45 minutes, let's change that to hours. How many hours is 45 minutes? Well, it's 3/4 of an hour. 3/4, 3/4 can also be written in decimal form by 0.75 hours. So if we times 30 by 0.75, get out my calculator, 30 times 0.75, that gives us 22.5 miles. That's how far east he moved. That's how far to the right this person moved. Okay, now let's do the same thing for this when he turned around. Okay, he was going 40 miles per hour due west for 60 minutes. Well, this one's easy because 60 minutes, how many hours is that? It's 1 hour. Okay, so instead of minutes, I'm going to put 1 hour. If we times the time by the speed, it will give us the miles that was traveled. And obviously that was 40 times 1 is 40 miles. Okay. So let me draw the vectors for this. Let's draw the vectors. Let me do it up here on the top. So when he went due east, he moved 22.5 miles. So 22.5. Then he turned around and went 40 miles. 40 miles due west. Okay? So if we're going to come up with a change in displacement, I need to know where his final displacement was. We're going to figure that up with vector addition here. So 22.5 is going to be positive because it's to the right. Plus, I'm going to put a negative 40. Why? Negative 40. Because he was going to the left. And in physics, a negative means to the left. So 22.5 minus 40 is equal to a minus 17.5 miles. Okay. So displacement final would be minus 17.5. Displacement initial, I'm just going to say he started at point 0, divided by the change in time. Now, how much time did this take? Well, it took 0.75 hours for that part of the trip and 1 hour for this part of the trip. So final time was 1.75 hours minus the initial time. Initial time is always 0 unless it tells you otherwise. Okay. So if we take this, a minus 17.5, and divide it by 1.75, you're going to get a minus 10. And what were we measuring in? Miles. And the time was measuring in hours. So a minus 10 miles per hour would be his average velocity. Now, can you really go a minus 10 miles per hour? No. What is the sign telling us here? The sign is telling us direction. So average, throughout the whole trip, he would have averaged 10 miles per hour to the left, or due west. Yes, and we got it right, so that they found the same answer that we came to, a minus 10 miles per hour. Okay, let's go to practice problem number 12. It says a car's displacement was measured as it traveled for the first 6 seconds, and the data is reported in the table below. Use the data to answer the following questions. So let's look at this. This is called a data table. So let's look at it for a second. It's got time here in this column, so 0, 1, 2, 3, 4, 5, and 6 seconds. It's got displacement measured in meters. So at 0 seconds, of course, it's going to be at 0 meters. But at 1 second, it's at 5. And then it goes to 17, 38, 59, 86, and 102 each second. Okay, so let's answer this question. On part A, it says, what was the car's average velocity from 0 to 2 seconds? If you look here, even part B is asking for average velocity. C and D are also. So let's write the formula for average velocity up here so that we can use it on each one of these. Average velocity, how do you find it? Well, it's change in displacement divided by the change in time. Okay? So we're going to do that for part A, B, C, and D individually. So let's do part A first. What was the car's average velocity from 0 to 2 seconds? Okay. Average velocity is equal to displacement final would have happened at 2 seconds. That was the final displacement, so it's 17. See where I'm getting that? So at 2 seconds, it was 17 meters away. That's his displacement final. Minus the displacement initial in this part would be at 0 seconds. The displacement initial is 0. Divided by change in time, so the final time would have been 2 seconds. And the initial time is at time 0. So 17 divided by 2, and that's 8.5. And what are we measuring in? Well, the displacement's measuring in meters, the time was in seconds, so this is going to be meters per second. So for the first 2 seconds that car traveled, its average velocity was 8.5 meters per second. Okay, let's go to part B and see how this continues. It says, what was the car's average velocity from 2 to 4 seconds? So again, I'm going to put average velocity is equal to, now its final displacement is going to occur at 4 seconds here. That's the final displacement. So at 4 seconds, it was at 59 meters. So I'm going to go 59, subtract the initial displacement would have occurred at 2 seconds. So if we go to 2 seconds, it was 17 was his displacement. Okay, divided by the final time would have been 4 seconds, minus the initial time of 2 seconds. Okay, let me grab my calculator. So 59 minus 17 is 42. Divided by 4 minus 2 is 2. So as you can see, we got 21 meters per second. So from 2 to 4 seconds, his velocity increased to 21 meters per second. Let's see what happens in part C, where it's from 4 to 6 seconds. So again, average velocity is equal to displacement final would have occurred at 6 seconds. 6 seconds, it was 102 meters away. And the initial would have occurred at 4 seconds. So 4 seconds, it was 59 meters away. Divided by change in time. So the final time would have been 6 seconds. The initial would have been 4 for that time frame. So 102 minus 59 is 43. Divided by 2 again. So 43 divided by 2 is 21.5 meters per second. Okay, so from 4 to 6, in part C, it was still increasing its speed a little bit. It went up to 21.5 meters per second. Okay, slide this out of the way for a second. And now let's do part D, which says, what was the car's average velocity from 0 to 6 seconds? So we're going to start at 0 and go clear to 6 seconds, the whole trip. Okay. Again, average velocity is equal to, let's see if we can get this out of the way, is equal to, the displacement final would be 102 at 6 seconds. The initial is 0 seconds this time, so it's 0 meters. Divided by time final, which would be 6 seconds, minus time initial is 0. So this is going to be 102 divided by 6. So 102 divided by 6, and that's 17 meters per second. Now let's stop and talk about what this means. So if you were talking about the motion of this car, at part A it started at 8.5, so it's going kind of relatively slower compared to the other sections. Part B, it's sped up to 21, and from 4 to 6 seconds on part C, it sped up a little bit more to 21.5 meters per second, and if you average the whole trip, it averaged 17 meters per second. So you can see his velocity increased from A to B. It also increased from B to C. So his velocity was increasing. Another way of saying that is that he was speeding up. Another way of saying it, again, is that it was accelerating. So this car was accelerating for the first 6 seconds. But average velocity for the entire trip, 17 meters per second. Okay, good job. Let's go to another slide. So average velocity versus instantaneous velocity. This is kind of the same thing as instantaneous speed that we talked about earlier, but instantaneous velocity refers to velocity at a specific time. It's got both speed and direction. So this graph, what it's showing you is position on the y and time on the x-axis. If you plot a position versus time graph, at time at point 1 and 2, it had this curve to it. If you wanted to find an instantaneous speed, you would have to find the slope of that line at a point tangent to that curve. Anyway, we won't get into it much more than that, but the tangent line through t1 would be the instantaneous velocity at t1. So if you wanted to find his instantaneous velocity right here, you would need to draw a tangent line, which barely touches it at t1, and then find the slope of that tangent line. Anyway, practice problem number 13. Determine whether the velocity of each car is positive or negative in each of the following. So we're looking at velocity and whether it is positive or negative in each of the following situations. Okay, let's go to part A. A car is moving to the east at 30 meters per second. So if it's going right, we talked about this last time. If a car is going to the right, it's going to have a positive velocity. Okay? B, a car moving to the west, it's going left. Well, if it goes left, it's going to have a negative velocity. So it would be negative 30 meters per second. C, a car is moving up or to the north at 30 meters per second. That's also positive. It's going up. In physics, up is positive. Okay, D, a car is moving down south at 30. So in physics, when you go down, that's negative. So just remember, if you go to the right, it's positive. If you go to the left, it's negative. If you go up, it's positive. If you go down, it's negative. Okay, let's talk about one final thing in this video. We're going to talk about calculating acceleration. Calculating acceleration. So acceleration, another way of saying that is speeding up or slowing down. So it's average acceleration. Here's the definition: is a change in velocity. So a change in velocity. So you're not moving at a constant velocity, you're changing. You're either speeding up or you're slowing down. Divided by the change in time. Okay? Well, velocity, let's look at the units here. It says that the units are meters per second squared. Meters per second squared. Let's figure out how they got meters per second squared. If you look at this formula down here, for acceleration average or average acceleration, it's equal to the change in velocity divided by the change in time. Well, velocity is measured in meters per second, and time is measured in seconds. So what's meters per second times 1 over seconds? That's meters per second squared, because seconds times seconds is seconds squared. So that's how they get the units of meters per second squared. Okay, acceleration can be positive or negative. Just like velocity, it can be positive or negative. Okay? Negative acceleration is called deceleration. So negative acceleration we call deceleration. Think about your car, driving a car for a second. If you press on the gas pedal, another name for gas pedal is the accelerator. So if you press on it, it's going to make your car go faster and faster and faster, or accelerate. If you want it to slow down, you're going to press on the brake. Well, the brake decelerates it. So think of it that way. The gas pedal is your accelerator. The brake pedal is your decelerator. So let's remember this formula. We're going to use it quite a bit in the coming slides. So average acceleration is equal to change in velocity over change in time. Acceleration changes, let me see if I can get this out of the way. Acceleration changes when you speed up, slow down, or turn. Now this is a tricky one here. When you turn, you are accelerating. Even if you're going at a constant speed, you're still going to accelerate. So let's say you go around a turn at 5 miles per hour, constant. So your speed isn't speeding up or slowing down, it's constant. But you're turning. Velocity, if you remember, is a vector quantity. It changes with direction. And so if you turn, you change direction, you're going to accelerate. So anyway, just something to think about. Okay, practice problem number 14. A cheetah, starting from rest, has an acceleration of 33 kilometers per hour per second. This has a few parts to it. Let's answer this first part. How fast is the cheetah running after 1, 2, and 3 seconds? Here's a good way of thinking about acceleration. So if this cheetah is accelerating at 33 kilometers per hour per second, it means that each second it's increasing its speed by 33 kilometers per hour. So after 1 second, it's going 33 kilometers per hour. After 2 seconds, it's going to increase it by that much again, so it's going to be 66 kilometers per hour. And at 3 seconds, I'm just going to write the 3 in right here, it's going to increase it again by 33. So that's going to be 99 kilometers per hour. So each second, it gets faster and faster and faster by this amount. 33 kilometers per hour. The answer here, yeah, let's see if we got it right. So yeah, 33 at 1 second, 66 at 2 seconds, and 99 kilometers per hour at 3 seconds. And 99 kilometers an hour, it says here, is over 60 miles per hour. So in 3 seconds, a cheetah can get going 60 miles per hour. That's pretty impressive. It's the fastest animal on the planet. Okay. This bottom part of the slide just shows how acceleration is equal to change in velocity over change in time. Velocity is measured in meters per second. If we times that by the time, 1 over seconds, you get meters per second squared. So if you ever see units in meters per second squared, you just know that is acceleration. Acceleration. Okay, so the units of acceleration. Okay, let's go to practice problem 15. It says a race car's velocity was measured as it traveled for the first 6 seconds, and its data is reported in the table below. Use the data to answer the following questions. Okay, again, we have this data table. Okay, the data table. It's measuring in time in seconds and velocity in meters per second. Time again, 1 to 6 seconds. Velocity is measuring from 0 to 92 meters per second. Now let's answer part A. It says, what was the car's average acceleration from 0 to 2 seconds? Let's write down average acceleration. How do you find it? Is equal to change in velocity divided by the change in time. So change in velocity over change in time. Now let's just plug that in on part A. Average acceleration. The change in velocity, that's final velocity minus initial velocity. And we're talking from 0 to 2 seconds. So its final velocity would have been at 2 seconds, would have been 19 meters per second. So 19 minus the initial would have been 0 seconds. So 0 at 0 seconds it was going 0. So initially it was going 0. Divided by the final time is 2 seconds minus the initial time of 0. So 19 divided by 2. So 19 divided by 2 is 9.5. And what are my units going to be? Meters per second squared. So 9.5 meters per second squared was the acceleration from 0 to 2 seconds. Okay, now let's go to B and find it from 2 to 4 seconds. Again, average acceleration. The final velocity would have been at 4 seconds. So at 4 seconds, it was going 54. Minus the initial from this time period would have been at 2 seconds, 19. Divide that by the final time would have been at 4 seconds, and the initial time for this segment would have been at 2 seconds. Okay, so 54 minus 19 is 35. Divided by 2, and that's 17.5 meters per second squared. Okay, 17.5 meters per second squared. Let's go to part C. From 4 to 6 seconds now. Okay. The final velocity would have been at 6 seconds, would have been 92, minus the initial would have happened at 4 seconds, 54, divided by final time is 6 minus initial time 4, so 92 minus 54 is equal to 38. Divide that by 2 is equal to 19. The units here are meters per second squared again. So 19 meters per second squared. And so D says, what was the car's average acceleration from 0 to 6? So we're going to average the whole time here, the whole trip. Average acceleration. The final velocity would have been 92. The initial velocity at 0 seconds is 0. The final time is 6 minus the initial time is 0. So 92 divided by 6 is equal to 15.3 meters per second squared. Okay, so let's look at what we just did there. We're noticing that the acceleration is increasing as it went from part A to part B and B to C. But the average acceleration for his whole trip would have been 15.3. All right, one final segment on this video. Let's do the signs of acceleration. So acceleration can either be positive or negative, and it's a little tricky here. So please pay attention to this part of the video. Determining the sign of the acceleration vector can be a little tricky. A car speeding up to the right is positive acceleration. So if this was the motion of the car, so it's going slow and then it speeds up, I don't know if you can see that, it speeds up to the right. That's positive acceleration because it's going to the right and it's speeding up. But a car going to the right but slowing down has negative acceleration or deceleration. So it's going fast and then it slows down for something. Okay, that's negative acceleration or deceleration. You'd have to press on the brake to do that. A car speeding up to the left has negative acceleration. So if it's going to the left and speeding up, that's going to have negative acceleration because it's going left, which is negative in physics. Okay, now here's a tricky one. A car going to, let's get this out of the way. A car going to the left but slowing down has positive acceleration. So if it's going to the left, but it's slowing, so it sees something and it slows down right here at the end and it slows down, that's called positive acceleration. It's decelerating to the left, so that's positive acceleration. So it's a little tricky. So as a rule of thumb, this is very important to remember. When the object is slowing down, the direction of the acceleration is in the opposite direction of the object's motion. So whenever you hit the brake, your acceleration is the opposite of the direction you're going. Okay, and this is a very good animation that kind of shows what's happening here. Watch this red ball roll down the track. And you're going to notice it has a couple of vectors here, a velocity vector and an acceleration vector. And watch what happens at the beginning. Let's watch it a few times. Get this thing out of the way again. You'll notice that when it slows down, the acceleration is opposite the velocity. When it's speeding up, it's going in the same direction. So let's see that. As it goes down, see, notice they're in the same direction. Now it's slowing down, acceleration changes. And again, it's slowing down, so they're in opposite directions. So let's go over this again. Let me say this again. When the object is slowing down, the direction of the acceleration is in the opposite direction of the object's motion. Okay, let's do a practice problem on that and see if we got it. How can braking provide both negative and positive acceleration? So let's say we go to the right, but we hit the brake right here. So we're going in a positive direction, but we hit the brake. Would that be positive or negative acceleration? Well, it's negative. We're hitting the brake. We're going in a positive direction, but if we hit the brake, it switches direction, so that's negative acceleration. And how can it be positive acceleration? If you brake and, okay, so let's say we're going left, which is in the negative direction in physics, but we brake. So we hit the brake right here. So we're going fast and then we slow down. Well, when we hit the brake, the acceleration vector switches direction, so it's positive. So by going and doing those scenarios, you can have both negative and positive acceleration. So the answer, if the brakes are applied when moving to the right, acceleration is to the left, and therefore negative. If the brakes are applied while the car is traveling to the left, the acceleration is to the right, and therefore positive. So hopefully that makes sense. B, how can you have a negative acceleration without braking? How can we have negative acceleration without braking? Well, just go left, but speed up. That's negative acceleration. The answer is you increase your velocity to the left. So you're going faster and faster and faster to the left. Okay, part C. Can an object experience acceleration while simultaneously having zero velocity? And the answer is yes. How can you have acceleration with zero velocity? Well, the answer is change directions. Okay, when you change direction, your velocity is changing because velocity depends on direction. And so yes, you can. You just turn around. Okay, practice problem number 17. Determine the sign of the car's acceleration in each of the following. Part A, a car accelerating to the right. Let me see if I can show you that on the board. So we're going slow and then it speeds up to the right. Well, this is going to be positive acceleration. Yeah, because we're going to the right and speeding up. That's positive acceleration. Okay, part B, a car accelerating to the left. Let me see if I can show that on the board. So we're starting here. We're going to go slow at the beginning and then speed up to the left. And so we're going in a negative direction and speeding up. That's negative acceleration. That's negative. Part C, a car slowing down while going right. Let me see if I can show that on the board. So we're going right, but we're going to slow down. We almost come to a stop. Okay? So we're going right, which is positive direction, but we hit the brakes. When we hit the brakes, what does that do to our acceleration vector? It changes direction, and so actually it's going to be negative. Even though we're going in a positive direction, when we hit the brakes, it's negative acceleration. Okay. Part D, a car slowing down while going left. Let me see if I can show that one. So if we start here, we're going fast and then we slow down as we're going to the left. So we slow down. Okay, so we're going in a negative direction, but if we hit the brakes, that makes it a positive acceleration. So remember, if you hit the brakes, it switches the direction of acceleration vector. Okay, I think we'll stop there. We've gone through a lot in this video. Let me just review what we've gone through. Speed. We learned how to calculate velocity. We learned how to calculate acceleration. Speed. Let's talk about that one for a second. Speed is equal to distance divided by time. Velocity is equal to change in displacement divided by change in time. And acceleration, we just got done, is equal to change in velocity all over change in time. So we're going to use these equations. Okay? please write them down somewhere. We got to memorize these. And we're going to use them on some of the worksheets in the book. So we can stop the video there. And what I would like you to do now is go to your workbooks, and you now know enough to do displacement, velocity, and acceleration worksheet number 1. Also, displacement, velocity, and acceleration worksheet number 2. Also, calculating average velocity worksheet. And also, calculating average acceleration worksheet. So there's quite a bit of work to do in the workbook with those worksheets. So if you need help, remember you can always watch this video again, go through those parts that you need help with. Good luck.